Thank you very much, Dr. Yokoi Sensei. Thank you very much to the public for coming to this lecture. Thank you very much to Dr. Miyake, that he was behind me a minute ago, for having invited me to come to Japan, specifically Kyoto. I was also in Tokyo a few days ago, teaching a course and giving a talk at a symposium invited by Professor Iwata. And also thank you to my former students and now a sensei at Virginia Tech. Gota Morota has been a very good company during this time to Japan. I'm deeply honored by giving this lecture. I'm deeply honored by your presence, and specifically in this building and hall with a very important name, no less than a Nobel Prize in Physics. So I will start by making a distinction between life and abstractions. This photo is of a very famous painter called Pablo Picasso. He was originally from Catalonia, Spain, and he introduced a concept of painting, of abstract painting, that was revolutionary in art. So this photo of Picasso became a self-portrait, and that's an important thing because it relates to many of the things that I've been telling you about the history of statistical methods in animal breeding and quantitative genetics, because they're mostly abstractions. So in agricultural sciences and also in medical sciences, we deal with traits that we call them complex. That is life. What is the reason for that? Is that the reason is life is the result of a very, very large number of biochemical reactions that are mutually integrated, and they act in a concerted action together with the environment to produce outputs that in agriculture we call them phenotypes. And we measure the outputs, but not necessarily the inputs. The inputs are not always observable. So in genetics, there is a concept that is that of interaction between genes, and that is life. But we normally use abstractions. But let me elaborate what do I mean by life versus abstractions. This is a very well-known cycle in biochemistry. It's perhaps one of the first cycles that you learn. It's called the Krebs cycle, the cycle of the tricarboxylic acids. And this is a cycle in which there are 12 enzymes that intervene, which are marked with an arrow. And if you remember, there's an old paradigm in genetics, one gene, one enzyme. So that implies that this cycle is controlled by 12 genes acting together, at least, maybe less, maybe more. So the abstraction that we normally make is that every time that we change a genotype at each of these genes that code for the enzymes, you add or subtract something to the output of the cycle, but that's not true. It suffices to do a knockout of any of those 12 enzymes and the cycle that stop. That's an indication that it's interaction. So life doesn't necessarily act by adding or subtracting from something, but rather it fundamentally based on the notion of interaction. So it must also be that the way that genes relate to phenotypes or gene products relate to phenotypes must follow some sort of nonlinear logic. And the reason is because enzyme kinetics is controlled by a nonlinear logic. We normally talk about the Michaelis-Menten theory, where the reaction rate, the speed at which a chemical reaction, biochemical reaction takes place, it depends on the concentrate. When the substrate concentration increases, the enzyme has to act faster, but it cannot increase its speed in an indefinite manner. So there is some sort of nonlinearity that is controlling the production of outputs from biochemical cycles. So because of this reason, and largely because even in spite of the revolution of molecular genetics, we still know very little about the genetics of complex traits. We tend to believe that there are many hundreds, if not thousands, of genes acting together. We tend to believe that for agricultural traits, most of the genes have a very small effect. And therefore, we try to come up with some sort of a mathematical description of the process. So, for instance, I hope I still know how to use these. The pointer is in the middle. We observe something. We postulate that there is some mathematical function that this depends on genetic variables and environmental functions. And if you think for a second, there is an infinite number of possibilities that I could come up for the form of a function. For example, here there are 5 of them, and we use actually the simplest one, which are linear representations of processes. For instance, here we could say that phenotype is a sum of genetic and environmental variables that may be independent and non-interacting. Whereas here, we could postulate that there is a joint effect of genotypes and environment that in animal and plant breeding is called genotype by environment interaction.